In this video, I'm going to talk to you about forces and motion. So a force is a push or a pull on an object, and we can have contact forces or non-contact forces. A couple of examples that we're going to be using in this video are a cannon firing a cannonball in space and a football resting on a field. So the first aspect that we're going to consider is when we have balanced forces. So if two forces are balanced, they have the same magnitude, but they act in opposite directions. And when we have balanced forces acting on an object, the object will not change its motion. So a stationary object will stay still, and a moving object will continue to move in the same direction and at the same speed. So here we have the example of the cannonball being fired in space. Now if that cannonball doesn't experience any gravity or any friction from any gas clouds, it will just keep travelling at the same speed and in the same direction forever. So there's no propellant, there's no rocket fuel, it's just an object with no forces acting on it, so there's nothing slowing it down, there's nothing speeding it up, and it will just keep moving in the same direction and speed forever. If we have a football at rest on a field, there's no motion, it's not moving anywhere, but there is a downwards force due to gravity, and there's also something that pushes back up on the football, and we'll come to that in more detail later, but that's referred to as the normal reaction force. So there's no net force on the football, so it doesn't move anywhere. So this relates to Newton's first law of motion, and we can sort of give this law the shorthand name balanced forces. Here's the Latin that Newton wrote for his first law. Fortunately, we have a translation. So an object at rest will remain at rest unless it's acted upon by an external and unbalanced force. An object in motion will remain in motion unless acted upon by an external and unbalanced force. Okay, so if we take this example of an aeroplane will have a forward force acting on it, which we refer to as thrust, a downward force due to gravity, a backwards force due to the air resistance, which we also refer to as drag, and an upward force referred to as lift. Now, if all these forces are balanced, then the aeroplane will continue to fly in the same direction at the same speed. And that's the consequence of Newton's first law. Okay, so the second aspect we're going to consider is unbalanced forces. So when two forces acting on an object are not equal in size, we say that they are unbalanced forces. Unbalanced forces change the way something is moving. They can make the object start to move, speed up, slow down, or change direction. So if we consider a rocket going into space, its motion is changing. It starts to accelerate upwards and away from the ground. And that's because the net force is upwards. So we've got the force of gravity pulling down on it, and then we've got the thrust pushing it upwards. And because the thrust is larger than the force of gravity pulling it down, then we get motion of the rocket. If we fire a cannonball just on Earth and we just watch what it does, because the forces are unbalanced, there's a backwards force of air resistance and a downward force of gravity, the object will slow down and change direction and eventually hit the ground. And this relates to Newton's second law of motion, which we refer to as unbalanced forces for shorthand. This states that the rate of change of the momentum of a body is directly proportional to the net force acting on it and the direction of the change in momentum takes place in the direction of the net force. So there's quite a lot going on there, and without making the full connection, without going into all the detail, the thing that we can take away from this, the important equation that we take away from this, is that force equals mass times acceleration. So there's a bit more that goes into this to make that leap, but we're not going to do that here. But when we talk about Newton's second law of motion, the important equation that we take away is force equals mass times acceleration. So if we look at our example of the aeroplane, in this situation the forces are unbalanced, and we've got arrows representing those forces, and because they're vector quantities, we can just move the head of one to the tail of the other, or vice versa, and work out the net force on the aeroplane. So if we move the tail of the drag to the head of the thrust, we can work out the overall forward force on the aeroplane. And if we do the same with the lift and the gravity, we can work out the overall upward force. Now we have these two net forces in the two directions. If we move the tail of one to the head of the other, we can actually draw in an overall force from the tail of one to the head of the other, and this gives us a right angled triangle. So we can actually use Pythagoras and trigonometry to get the magnitude of that net force and the angle. Okay, so this leads us on to Newton's third law of motion, which we can give the shorthand equal but opposite forces, and this states to which every action or force applied there is an equal but opposite reaction, i.e. an equal force applied to the object but in the opposite direction. So this brings us back to the idea of the football. So there are two forces acting on this in equal and opposite directions, and it means it has no motion. So let's consider the normal force. The normal force is the force that any surface pushes back up with. It can also be referred to as the normal reaction force, and it's given the symbol capital R. So that football at rest is pushing down because of the force of gravity acting on it, and the ground is then pushing back up on the football to the same magnitude but opposite direction, so the net force on it is zero. This leads us on to consider weight, and that's the force on an object due to gravity, and the equation for this is W equals mg. G is the acceleration due to gravity, which on Earth is 9.81 meters per second. Sometimes that gets rounded to 10 meters per second squared. In space it's 0, on the moon it's 1.625 meters per second squared, and so it depends on the location of the object. The other factor then is m, the mass of the object, in kilograms. So overall, that's been a video about forces and motion. I hope you found that useful. Please remember to like, comment and subscribe, and thanks very much for watching.